and welcome to another video. My name is Iris and I am a postdoc at the German Aerospace Center where I study Venus. I thought today would be a great day to tell you something about the research that I'm doing. No, this does not completely come out of the blue because I am actually attending a conference, LPSC, which I believe stands for Lunar and Planetary Science Conference. I'm very well prepared. I am attending that conference. I have a poster there. Well, I say attending. I am here. I am attending because it's actually in Texas. Anyway, I am there in spirit. I've made a little poster, but because it is a US conference, you know, the time zones aren't great, so I am meant to present my poster from 1:30 a.m. until 3:30 a.m. Chances are that I'm not that lucid when I do that. So I thought I'll just make a little video explaining what I do, and hopefully that's useful and more fun, and yeah, it can serve as an excuse if I fall asleep by the time that I'm actually presenting my poster. So what do? I am interested in the evolution of Venus. Usually, you know, I'm quite interested in the interior of the planet. So how does the mantle work? How does the crust of Venus work? But with this topic, I am specifically interested in the interaction of that interior with the atmosphere of Venus. Because Venus has a very thick, heavy atmosphere. This atmosphere can influence the interior, and that works in some kind of feedback loop that I will briefly explain to you. You have your atmosphere, and the components of the atmosphere, as you might well know, determine how hot the surface is. You know this from Earth with this whole climate change problem and the fact that we have more and more carbon dioxide, which is a greenhouse gas in the atmosphere, and that means that the surface of the planet heats up. Now, Venus has a lot of carbon dioxide. I think it's about 93% carbon dioxide in its atmosphere. You can imagine, you know, the surface of Venus very, very hot. But the temperature of the surface affects what happens inside the planet, because the way the crust and the mantle of a planet move depend basically on how it can cool, because that is all that drives motion in the mantle and in the crust of a planet, just cooling basically. And you have different types of cooling. You can have cooling due to conduction, or you can have cooling due to convection, when things start mixing. Maybe this is the point where you realize I haven't actually prepared a pitch of what I wanted to say. I'm just kind of rambling as if I'm giving a poster pitch. I'm sorry. So if the happenings of the interior of the planet are determined by how it can cool, you can imagine that the temperature at the outside of the planet is very important, because, you know, if that's a very high temperature, it will cool less. And if it's very cold, then it's, you know, there is something cold against something hot, it will cool more easily. It's very simple. Bear with me. So the temperature of the surface is affected by the composition of the atmosphere, and the temperature of the surface affects what happens inside the planet. Now, what happens inside the planet determines how much volcanism you have, for example, and how much melt pockets there are inside the crust and find their way out through, well, for example, volcanism, or volcanism within the crust. Could also be. And in that melt, there are so-called volatiles, which are very light elements. And these volatiles get outgassed, so they get they get thrown out of the interior of the planet when there is, for example, a volcanic eruption. Together with rock, you also have gases that come out. And those gases obviously make up of the atmosphere. So the composition of the atmosphere is in turn determined by what happens inside of the planet, because of how much volcanism and how much outgassing you have. So then we have this nice closed loop. Great. How on earth am I going to study that? That is the question I asked myself about 6 months ago, because I didn't know, but other people, thank God, have looked at this a lot before. The way I approach this, I mean, there's many different ways of approaching this, but the way I approach this is by numerical models, because that is kind of what I know how to do. And the model that we are using, the code that we are using, is called Gaia, which is the DLR in-house code, and it is made to solve for the thermal evolution of the planet, so for the cooling of the planet, the cooling of Venus, if you will. What it didn't have was that loop with the atmosphere. So that's where I came in, and I had to add that to the Gaia code. Add a way to see how much of the different gases are outgassed and how that then affects the temperature, and use that as a boundary condition for our model. Great. Not that difficult, because all of these things have already been done by the people I will list here. Editing, Iris. Do your thing. If that didn't work, it's going to look very awkward. What did I do? Well, I took the ingredients from different papers, different ways of doing things, and combined it all in my own little add-on, if you will, of the Gaia code. And there were several things that I've been looking at. For example, saturation curves. If that doesn't mean anything to you, no worries. It also didn't mean anything to me 6 months ago. But basically what it means, you can have volatiles being inside of the melt and wanting to escape, but not necessarily all of them go into the atmosphere if you assume that your melt reaches the surface. Some of them might just stay inside the crust, and that depends on the saturation concentration of a certain gas already within the atmosphere. So you need to kind of calculate what that would be and then compare to what you would outgas from the melt, and then see what you actually outgas. I have a panel on my poster, if that makes sense. And here are some figures, because you can make saturation curves for water and carbon dioxide. Those are the only two species we are considering at the moment. You can have a look at what it is, the saturation concentration, with your atmospheric pressure. I thought this would be theoretically not that difficult, but the way we went about it is that we use Volatile Calc by Newman and Lowenstern, 2002, and they made a model that works where you can actually calculate your saturation curves for carbon dioxide and water. So, on the surface, that is great. However, that model is an Excel file written in Visual Basic, and my laptop did not like that at all. Nor did I, because it was very difficult to figure out exactly what was being done. But in the end, I managed. It all worked. Turns out it doesn't really matter what exactly the saturation concentration is, but in any case, I was able to reproduce Newman and Lowenstern 2002 and recreate their saturation curve. So that was great. And these are the figures that belong to that. We kind of sorted that. Another thing that I needed to figure out as well, of course, was how does atmospheric composition influence the surface temperature? That's kind of what we are going for here. So for that, I used some equations from Hönig et al. In 2021 that also kind of seemed to work. I could reproduce everything that they did, so that is great. Well, I say everything, I mean the equations worked, like those few equations. My calculation from atmospheric composition to surface temperature worked. Just to get an idea of how things worked exactly, I looked at, within these few equations, how certain parameters would affect the surface temperature. So I looked at how the partial pressure of carbon dioxide affects the surface temperature, the partial pressure of water, but also the solar influx and the planetary albedo. Albedo? I think albedo. And they all affect the surface temperature in different ways, which you can read more about on the poster if you are interested. Now, you can imagine my excitement. All these kind of building blocks individually checked and, benchmarked to death. It all worked. So I put it all together just last week in preparation for my LPSC poster, where I could finally look at some actual evolution models. And then did everything blow up in my face, and did it have lots of nuns, not numbers, and then, also have minus infinity and plus infinity, and did it crash and burn? I mean, yes, but at least I thought it would work. So that is kind of the state of affairs at the moment. I believe that every single building block worked, but together it does not. So that is ever so slightly sad, and that is why there is no great evolutional model on the poster. It's very much still a work in progress, and I'm very happy that I put the word towards in my title because I'm very much still working towards it. The first thing that I'm going to do is figure out where those nuns come from and why it is blowing up. I think there's something wrong with the masses that I'm tracking because I need to also account for there only being a limited amount of water in the mantle, and at some point that needs to be depleted and then there is no more water anymore in the mantle. But at the moment I'm getting like negative masses, and that is never a good thing. So I'm looking into that. And then once I figure that out, I can tell you what other things we are working towards. The ideal goal is to also include other species, not like animals, if you're still watching and you have no clue what I'm talking about. Chemical species. So at the moment, as I said, we have carbon dioxide and water, but what about all the other things? You can have carbon monoxide, you can have OH, which is hydroxyl. Can you tell I'm not a chemist? The more species you include, the more realistic your atmosphere will be. Certainly the more complex it will be. The more influences you can have on the surface temperature and hence the interior. So that is kind of where we would like to go. Luckily, there's still some time to get there. I hope this was somehow illuminating and or fun to watch. If you have any questions, feel free to ask. Don't worry about it being midnight. Maybe I will see you around at LPSC. Hope you have a lovely time. Bye! I forgot the word for oxygen for a minute.